So it's my pleasure to introduce Dr. Evelyn Powell, who is visiting today from Lamont-Doherty Earth Observatory. She is a postdoctoral research associate there, working primarily with Jackie Osterman and doing deformation, geodesy of the Earth, and how we can backtrack sea level effects in the past, and I imagine looking in forecasting into the future. Before Lamont, she did her PhD at Harvard, working with Jerry Mitrovica, and I don't know the name, but the papers that have come from your dissertation look at West Antarctic ice sheet and what would happen as the ice has moved near field and far field. And before that, she got a dual major from the University of Texas at Austin, one in physics and the other in liberal arts, and probably archaeology based on some of the things we talked about last night. And I think we will hear about some of that today. So without further ado, let me introduce Dr. Evelyn Powell.
Hi. Fantastic. Can everyone hear me okay online? Is that good? Yeah? Okay. Great. All right, thanks all. Thank you for the introduction. Perfect, okay. Hi, my name is Evelyn Powell. I'm a computational geophysicist located just across the George Washington Bridge, sat in Manhattan. And I thought I'd use some time here to tell you about some of the sea level work that I've been doing, ranging from resolving tribal land disputes in Canada to inferring Earth's viscoelastic structure in the West Antarctic in particular. I've been pretty laser focused on West Antarctica. Before we get into that though, so this picture is my favorite sea level marker. I think everyone should have a favorite sea level marker. It's called Celsius rock. And Celsius, who's better known for the temperature scale, was a Swedish scientist who was tasked with sorting out how much Sweden, the sea level was falling in the Baltic Sea. And he connected with social scientists, and he used taxation records from the 1580s. So he was doing the survey in 1730, and he used taxation records of the seal rocks, where seals used to perch, because that's next to sea level, to infer the fall of sea level 200 years later. And it was pretty significant, right? So I'm going to put, for scale, someone of height 5'2", which is how tall I am. So there's a pretty substantial amount of sea level fall that we can see from 1731 to 1831 to 1931. So he carved on this island in Sweden a line in 1731 for future scientists to be able to revisit and see sea level in the future. And this theme of the island's emergence from the sea is going to be a theme that we'll come back to in a bit. Okay, so to start with some motivational background though, I like to start with this and say that polar ice sheets are losing mass. The figure at left shows the broad pattern of ice mass loss in Antarctica, inferred from geodetic measurements such as those made by the gravity satellite mission, the GRACE satellite mission. And the West Antarctic ice sheet, I don't know if you can see my cursor. Here we go. So the West Antarctic ice sheet is losing mass, and this mass loss is accelerating. And this is important because the West Antarctic ice sheet, WAIS, I'll use that acronym a lot, WAIS alone is thought to contribute between 3 to 4 meters of sea level rise. So that's 3/4 of a one-story building or a full one-story building, right? That's quite a substantial amount of sea level rise in the West Antarctic ice sheet. And the figure at right is flooded Texas coasts if sea level did rise by 3 meters. And I'm from Texas, so we are talking about sea level changes that are arising due to our dynamic cryosphere today, as opposed to ocean dynamics, for example. We're talking about the cryosphere. Okay, so quick outline for my presentation. So we're going to talk about some sea level modeling, some of the background, and then move on to 3 case studies, 1 in Canada and then 2 in Antarctica. And then I'll touch on some of my research vision at the end. All right, so let's start with some background on sea level modeling. When you model sea level changes, there are three key players. So these are the oceans, the ice sheets, and the solid Earth, upon which those two masses rest. So let's go through these in turn, and starting with oceans. So water is a liquid, and a liquid takes the shape of its container and maintains an almost fixed volume. And you may recall these properties from the delightful Ig Nobel Prize, which demonstrated that cats are liquid. Okay, so oceans take the shape of their container, and in this case, the container is set by the ocean basins and the gravitational equipotential surface that corresponds to mean sea surface height. So with this framework, we can define a global sea level field, which is the height of this gravitational equipotential surface minus the solid Earth surface. And the ocean water will fill its container, which exists anywhere that the Earth's surface is below that gravitational potential surface, and there isn't a pesky ice sheet in the way. Okay, so let's turn to the ice sheets. So we know from proxies for ice volume, such as what's being shown in this figure, which is Delta 018 from benthic foraminifera, from Mosecki and Ramo 2005. So we know that global ice volume has not been constant through time. I should say that time moves towards the present on the x-axis here. And what you can see is this global pattern of ice sheets waxing and waning, growing and dying out, where they have, for example, 21,000 years ago, ice covered much of the northern hemisphere. So we would have been underneath quite a bit of ice sheet here in New Jersey at that time, 21,000 years ago. Okay. So finally, let's turn to the solid Earth. So the manner in which the solid Earth responds to an applied forcing, it's going to depend upon the time scale of that forcing. So I'll give some examples relative to this sort of schematic forcing timescale axis. So on forcings that act on short timescales, so like tides, for example. That's the animation. All right. The Earth's response is considered elastic. So the strain, the entirety of the strain is entirely recoverable. In contrast, for forcings that act on much longer timescales, so millions of years, such as thermally driven mantle convection, the Earth's response is more like a viscous fluid, so like honey, for example. And it turns out that the isostatic adjustment to ocean and ice loading, that occurs on intermediate timescales. So moving that to the side. So the Earth's response to this surface loading forcing, it's in a manner that we consider viscoelastic. So there's both a time variable viscous component as well as an instantaneous elastic response. Okay, so our ability to understand past sea level changes, as well as predict polar ice sheet contributions to future sea level rise, it depends on our ability to accurately model the solid Earth's response to surface mass loading, right? And so this deformational, gravitational, and rotational response to the H2O mass exchange between locked in solid ice form to distributed as liquid in the ocean, that is termed glacial isostatic adjustment, right? So for example, heavy ice sheet that covered Canada 21,000 years ago, it perturbed the Earth's surface. So it led to deformation of the solid surface where that heavy load pressed down and the crystalline mantle creeped outward from the center of that loading region and formed what are called peripheral bulges, right? As the climate changed, the ice sheet melted away and global sea levels rose because there was more water to be accommodated, there's more liquid water. But additionally, there was a globally variable sea level change as the solid Earth changed shape. So as the peripheral bulges collapsed because the crystalline mantle creeped back through dislocation mechanisms or diffusion mechanisms of the crystalline lattice. And you see that there is this pattern of sea level change and sea level fall and rise that occurs today locked into what occurred because of the last ice age. So this is absent any additional changes to our climate system. So for example, on the East Coast, we are experiencing about 2 millimeters per year sea level rise due to the collapsing peripheral bulge because the solid Earth is sinking. because the mantle is moving, right? And this is absent any additional melt. Okay, so why does GIA matter? Let's dig into that a little bit. So we need to understand sea level, past, present, and future. Let's start on the sea level side of things and ask the question, what would happen if the West Antarctic ice sheet, WAIS, suddenly melted, right? Suddenly is a clue. We would expect the Earth to respond elastically because it's quick forcing. So we're going to compute what's called a sea level fingerprint, where we uniformly shave off the top bit of ice from the West Antarctic ice sheet, and sufficient to raise global mean sea level by 1 centimeter. So if we distributed that shaved off piece of ice over the global oceans today, it would raise them by 1 centimeter. Okay. And what we see is that in the near field, so proximal to that ice sheet in that melt zone, we have a sea level fall, and a pretty substantial sea level fall. Global mean sea level is 1 centimeter, and we see excess of 10 centimeters in the near field. That's due to two effects, right? You have rebound of the solid surface because there's heavy ice sheet, this massive ice sheet is lessened, so it doesn't push down as hard. But also there's a gravitational effect where that massive ice sheet, in the literal mass sense, was pulling the ocean towards it. I think of it as like a magnet that's pulling the ocean towards it, and it loses strength. That magnet loses strength, so the gravitational field also falls. Okay, so that's what happens in the near field. But we know that mass is conserved, right? So that means that it has to rise more elsewhere in the far field. So now what I'm showing is the far field sea level change. And you can see that those of us who live on the East Coast, for example, we experience 1.3 times the global average sea level rise. So sea level doesn't rise up and down like a bathtub. It's geographically variable, and it depends on where the ice is melting and where you're sat on the world. Okay, we also care about GIA because it provides important constraints on the viscosity of Earth's mantle, which plays a fundamental role in the long-term evolution of the Earth system, right? So over timescales that are associated with mantle convection, the 3D viscosity field controls things such as the long-term thermal history, the planform of convective flow, as well as the stability of the rotation axis. The issue, however, is that viscosity of the mantle is difficult to constrain in the lab, right? So for context, I'm going to pull from another Ig Nobel Prize, which is the pitch drop experiment, which is the longest running laboratory experiment on the planet. So the pitch, this otherwise solid material, forms a droplet approximately once every decade. And so scientists use the timing of the formation of the droplets to constrain the viscosity of the pitch to about 10 to the 7th Pascal seconds. Neat. But in contrast, the viscosity of the mantle is thought to be in excess of 10 to the 20 Pascal seconds, right? So humans just are not long-lived enough to make such observations of olevine's fluid-like flow in the lab. Instead, we can use the Earth as a kind of natural laboratory and use observations of the GIA process to constrain the mantle's viscosity to ice changes that occurred on timescales that now lead to deformation today. Okay. Quickly, when we think about modeling sea level, when we think about doing GIA modeling, we talk about the Earth in two different paradigms. So the first, we think about the mantle as a 1D onion skin view, radially varying structure, where the mantle's viscosity only varies with depth. There's benefits to that. There are semi-analytic software codes that can solve this quite fast, right? So if you use a laptop, it'll be done in a few minutes. But we know that the Earth's structure doesn't vary just with depth. So we have inferences such as from seismic tomography, which is shown here from S40RTS on the right, that Earth structure varies laterally as well. And if we infer a thermal origin from the VS variability here, that would imply viscosity contrasts that vary on orders of magnitude, right? So in which case, if we want to think about the Earth where the lithospheric thickness, that top layer of the solid Earth, and the mantle viscosity, and we have it vary laterally, we have to turn to more computationally expensive techniques, right? So you have to turn to either finite volume, spectral element, finite element solver. But what I hope to convince you of today is that it is important and worthy of interrogation. Okay, so let's turn to our first case study. we are talking about Akimiski Island. So the map at left here shows the rough range of tribal lands at the time of European contact. And you can see the Cree, let's see if I can get my cursor here, the Cree here in blue near Hudson Bay and James Bay. This study focuses on Akimiski Island, Canada. It's the largest island in James Bay. It's delightfully taco-shaped. I'm Texan, I love this. It has a boreal forest setting, which you can see from the satellite photo, as well as the wildlife that's currently present. And it is the ancestral land of the James Bay Cree. Okay, so now I'm showing a present-day political map of Canada. And I want to be quite explicit and say that present-day Canada was created through land acquisitions. Right, so Akimiski Island, again boxed here, was incorporated by the Canadian government into the Inuit territory, Nunavut, in 1999. However, the James Bay Cree maintain that they have never relinquished their claim to Akimiski Island through treaty or any other means, right? So herein lies the problem. Two Canadian Indigenous groups lay claim to Akimiski Island. The Inuit through the Nunavut Act of 1993, which is shown, the signing of it is shown in here in the photo between Brian Mulroney, the Canadian Prime Minister, and Paul Clausa, the then head of the Inuit territory. And also the James Bay Cree through Aboriginal title. Okay, which is the collective right to the use of and jurisdiction over a group's ancestral territories. Right. So this dispute can be settled because a common law test for the proof of Aboriginal title exists in Canada. However, through its inaction, the Canadian government switched the burden of proof from the Inuit to the Cree. So it behooves the Cree then to prove accordance with the 6 criterion for the common law test of Aboriginal title. And what remained to be proven at the time when I was brought on board was accordance with criterion 2, which is that the occupation of the territory was sufficient to be established at the time, since time immemorial, which is traditional use and occupancy was an established fact at the time of assertion of sovereignty by European nations. So for the common law test then, the Cree had to prove use and occupancy pre-European contact about 400 years ago. And you may be wondering, why are sea level modelers involved? Well, so it turns out that one prevalent story in the Cree oral history talked about how Akimiski Islands emerged from the sea. So according to Cree oral history, the Inuit actually first occupied Akimiski to hunt seals when it was first emerging. However, the Inuit later abandoned Akimiski because the number of seals decreased as the evolution of the island habitat occurred, and or the Cree fought them off. And what's unknown is the timing of these events. And more to the point, when did this island emergence occur, and was it pre-European contact 400 years ago? So to answer this question, we modeled sea level changes in James Bay, Canada, associated with the last deglaciation. And so for our modeling, for our geophysical sea level modeling, we require 2 inputs. We need a spatiotemporal history of ice cover, so some outlines of the Laurentide ice sheet, which used to cover Canada here, is shown on the left. And we also need a model of Earth's 3D viscoelastic structure. And so we performed 10 simulations with different 3D ice model pairs, and one from S40RTS is shown here on the right. Okay. So we ran 10 simulations, and the modeled sea level has to be constrained by present-day observation. So we have to match the present-day shorelines, and we also have to fit the observed crustal uplift rate at the nearby Moosonee site. We felt very lucky that there was a GPS site so close by to our study area. So that was great. Okay. We also have to verify that our models fit the available data. So this is sea level data, both index and terrestrial and marine limiting data in the James Bay region, with sea level relative to present on the y-axis and time with thousands of years before present on the x-axis, with time moving towards the right. And you can see a broad pattern of sea level fall over the last 8,000 years. And the different colored lines here are different simulations. And we were satisfied with our fit to the available data. And so we then turned to asking or getting the answer to our original question, which was, when did Akimiski emerge from the sea? Okay, so I'm going to show paleotopography predictions for just the one simulation here. The dotted black line is the present day shoreline of James Bay. And you can see in this first panel that 2,500 years ago, Akimiski Island did not exist. We have all blues. But if we step forward 500 years and you squint, you can see the first sliver of green, right? So at this time, Akimiski would have been a sandbar, which would have been favorable to seals. If we step forward another 500 years, we can see the areal extent increasing, and this would have been sufficient time for the ecological habitat to transition from a sandbar seal habitat to more of a boreal forest setting. Akimiski reached 50% of its areal extent about 1,000 years ago, continued to emerge to its present-day shoreline. And so we estimate, on the basis of this simulation, that Akimiski first emerged from James Bay at 20-30 years ago, which is certainly pre-European contact, right? 400 years ago was our benchmark here. And then the other 9 simulations were in accordance with this as well. So I'm showing on this plot the predicted emergence date in years before present for the different simulation numbers. And you can see that although there is some spread, which we would expect, all the simulations predict island emergence at around 2,000 years ago. So some takeaways from this first case study. Cree oral history describes the emergence of Akimiski Island from the sea. And we were able to, with our sea level modeling, quantitatively support their claim and timestamp the emergence of Akimiski to 2,000 years ago to establish this criterion for sufficient occupancy of the Aboriginal title. And this was published with a good number of people. And I want to say, I've talked about the sea level side of this, but so much more went into this study. So Zachariah General was a co-author and is the lead of the Indigenous group, and such important work was done in the interviewing with the Cree elders, so collecting the oral history in a culturally appropriate format. So if you want to learn about how the written record and the oral history converged, a lot more went into this paper than just the sea level side. So the Cree now have sufficient basis to enter into the recognition and implementation of Indigenous rights for Akimiski Island. So that's so inspiring. Oh, and just to close with a bit of color, so Akimiski the name is Cree. It's derived from Cree words, from Aka, which means land, and Aski, which means across. So there's a land across from here. That taco-shaped island is just across the water. Okay, so let's move on to our second case study. We're going to think about what would happen if the West Antarctic ice sheet collapsed in Antarctica. So for Antarctica, regional seismic tomography models are providing unprecedented images of the upper mantle structure. So this plot here is taken from Andrew Lloyd's adjoint-based work, adjoint tomography, showing variations in seismic wave speed at 125 kilometers depth. And you can see a dichotomy between east and west Antarctica, where the faster wave speeds in the east correspond to this older, colder, cratonic-like region, whereas in contrast, the West Antarctic is evidenced by thinned lithosphere, underlain by an inferred thermal upwelling, so this Cretaceous failed rift system with active volcanism. Okay, so this 3D structure has been shown to affect ice sheet evolution. It's been shown to affect the GIA corrections that you have to make for geodetic measurements of the present-day mass fluxes from Antarctica. And it also affects the sea level predictions that you would make in this region, which is what I'm going to talk about right now. Okay, so Antarctic's mantle structure, we accept, is highly complex. And we want to know, how would it affect waste collapse sea level predictions? And given that 1D techniques are so much more computationally efficient, how effective are they at capturing the sea level signals recorded in the far field where people live? So those are our 2 guiding questions here. So we're going to consider this ice flux scenario where we have an incomplete but substantial collapse of the West Antarctic ice sheet occurring over a 6,000 year time period, where the volume of ice would be sufficient to raise global mean sea level by 2.7 meters, this ice above flotation criterion. And the plot here is showing the thickness of the ice sheet at the end of the simulation with the present day shoreline of Antarctica plotted in red. Okay. In order to do this modeling, we need to first create our Earth models, especially from the seismic tomography inferences. So we're gonna create some 1D viscoelastic models as well as some 3D viscoelastic models. We are going to apply the forcing using our finite volume software here with the high resolution grid as shown in the figure here. We're very proud of how high resolution we can get our GIA modeling software in regions of interest. So this green line corresponds to this transition between sort of our global grid to our high resolution grid with spacing in around 2 kilometers in this region. Okay, so we're going to generate for each model global mean sea level predictions as well as geographically variable sea level predictions. So let's go through it. So we need to construct our 3D Earth models and our 1D Earth models. Here are the ones we're going to look at. For 1D, we're testing a sort of upper mantle viscosity that's on the lower end of what's considered feasible and one that's on sort of the more average end of what's considered feasible. But the main thing you need to think about is one slightly lower, one slightly higher in terms of viscosity. Similarly for the 3D Earth model, we test 2 3D Earth models. One where we have a lower conversion from seismic wave speeds to viscosity contrast and one where we have a more amplified. Main thing to take away from this figure is that the viscosity is much lower in model 3DB than it is in 3DA in the West Antarctic region. Okay, but generally we see the same sort of structure in our inference of viscosity. Great, so let's melt the ice sheet. What do we get? Okay, here's what we find. So what I'm plotting here is the global mean sea level prediction for our 4 different Earth models with time on the x-axis, so our full simulation is 6,000 years. And you can see that for the Earth models that have a lower mantle viscosity, they predict a higher global mean sea level, right? So the red line is our lowest viscosity in the upper mantle, model 3DB, and it predicts in excess of 3 meters of sea level, global mean sea level rise instead of 2.7, right? So why is that the case? So when you have GIA-driven uplift of marine-based sectors, so these regions that would otherwise be open ocean if there wasn't an ice sheet in the way, as the Earth continues to isostatically respond to the removal of that mass pressing it down, what you're going to have is water being pushed out into the open ocean even after the ice has completely taken away, right? In the event that you have low viscosity structure in the mantle beneath this uplifting region, what you're going to have is increased amount of water expulsion, which would potentially not be included in the sea level budget otherwise. And this was a major finding of a paper just prior to this one, looking at how much more the West Antarctic could contribute to global mean sea level, and we revised the estimate from 3.2 meters to 4.2 meters, so going from 3/4 of a 1-story building to the full 1-story building because of this water expulsion effect, right? So that was a finding that we were anticipating and we found again, and that was good. However, people living on the coasts, we don't experience global mean sea level, right? We experience the full geographically variable signal. So what I'm showing here is a prediction from our 3D model with the sea level change at the end of the prediction in orange to purple on the left-hand side, and then the residual where we removed the prediction from the 1D model in blue to red. And what you can see, and what I want you to take away from this, is that the far field sea level change where humans might live is actually lower for this less viscous model, despite the global mean sea level model, the global mean sea level being significantly higher, right? And moreover, if we look at specific sites, if we look at the different colored lines here, we can see that the variability between the 3D models is location dependent. And then if we compare the solid line to its corresponding dashed line, the variability is also location dependent. So how effectively a 1D model can capture the signal depends on where you are, right? There isn't a consistency here. So why is that the case? Well, so there are different sources of variability in the collapsed sea level signal. And in particular, we're looking at water siphoning. So as the ocean basin changes shape, you are creating new accommodation spaces for the water to go. And in particular, there's going to be continental levering around the far-field continents, but the big signal is due to the collapse of the peripheral bulge right next to the West Antarctic ice sheet, right? So there's low viscosity underneath that mantle too. And so it's also moving very fast and lowering and subsiding and leading to a very large accommodation space for the water to then siphon into and take it from the far field. So to wrap up this case study, we were investigating the effects of Antarctica's 3D mantle structure on sea level predictions of the West Antarctic ice sheet if it collapsed. And we found that the global mean sea level was previously underestimated. And this is due to this water expulsion mechanism and the low viscosity below waist, directly below the ice sheet. However, the contribution to far field sea level change, where people live, is potentially overestimated. And that's going to be due to this structure-dependent water siphoning and the low viscosity, mantle viscosity next to waist, right? So we argue that the analyses of past and future sea level need an accurate 3D mantle viscosity input and a more nuanced understanding of this cover history, right? Because both of these are going to be controlling what the sea level signal will be. All right, so if you're interested in learning more, this is discussed in these two papers I talked about here. And let's move on to our final case study. Hopefully by now, I've convinced you that the mantle viscosity structure beneath Antarctica is important and worthy of interrogation. Unfortunately, the conversion between seismic wave speeds to viscosity is highly uncertain. So the viscosity is going to depend on the rock microphysics considered. And the parameters that are involved in those conversions are highly uncertain, not least because, as I mentioned, like humans are not long-lived enough to make such measurements in the lab. But also, many of the relevant parameters, like grain size, the water content, they're simply not known. We don't have samples of the mantle from 450 kilometers down, right? So from the same seismic tomography model shown here, using different conversion parameters, we can get the viscosity inferred vary by orders of magnitude, okay? So we want to narrow that down because that really matters. We do have an additional and arguably underutilized resource at our disposal to improve our constraints on the mantle properties and the viscosity in particular. So we can use observations of the GIA-induced crustal deformation via the Global Positioning System, GPS surveying, to constrain the mantle properties. So this is showing a GPS station in Antarctica with courtesy of a penguin next to it. And you can see the circles on this map show the location of GPS stations that are installed in the West Antarctic. Okay, with pretty good coverage, honestly, for the continent. So there are published inferences of the mantle viscosity, 1D structure, from GPS based on deformation observed in this region. And taken at face value, they suggest pretty significant variations in mantle viscosity. So the estimates are going to range from around 10 to the 18 Pascal seconds to an excess of 10 to the 20. Okay, so Antarctica's mantle structure is highly complex. 3D GIA modeling is highly computationally expensive. We asked the question, are Antarctic GPS data sensitive to 3D mantle structure on these timescales, on these sort of decadal timescales where we're able to make these sorts of measurements? And we performed a sensitivity study. Yes, they are, especially the horizontal component of deformation. Okay, that's good news. We can use it, fantastic. So the next question, how effective is this technique for inverting or inferring or imaging this 1D viscosity structure? And the answer for that one's a bit more nuanced. it constrains the portion of the mantle that deforms, right? So previously we were thinking about these inferences as giving an estimate of the bulk average structure right underneath the station. And that's really not the case. If you have a 3D structure model and there's a pocket of lower mantle viscosity, and that's the portion of the mantle that deforms, that's what the GPS is going to tell you about, right? So in the case that you have 3D structure, you're not getting an average view of what the mantle is. You're getting a view of the portion that deforms. So that was kind of a paradigm shift in how we think about using these inferences. Okay, and really what we want to know, if we want to use this data set, and we do want to use this data set, we need to think about how to rigorously determine where GPS observations sense the mantle, right? And in particular, our group is working towards building the ultimate goal, building a 3D structure model where we jointly invert seismology, geodesy, and sea level data sets below the Antarctic. Okay, but we want to use GPS in Antarctica. How do we compute this data sensitivity? So asking the question, if we perturb the viscosity in some given grid cell, how will the uplift rate change at a station elsewhere, right? If we perturb it, grid cell over, or over, or over, how does each of those perturbations lead to a change in the observed uplift rate? The standard approach is to use finite difference techniques, and this is done in the early literature to good effect, especially for 1D inferences. The problem, though, is that it requires many forward calculations, so n plus 1, however many grid cells you have plus 1. In the case where you want to use a 3D Earth structure model, you're looking at in excess of 1 million calculations. So that is simply not feasible. You cannot do this kind of finite difference interrogation of the mantle structure using this finite difference approach. Something that's so exciting is this new development in the mathematics of the problem, where we are able to directly calculate this sensitivity field, these partial derivatives, how much the uplift change with respect to the viscosity change, via a method technique that only requires 2 simulations, a forward simulation and an adjoint simulation. This has been used to great effect in seismology. So we have adjoint seismology techniques that are very far in the field, but the equations for the sea level problem were only recently derived in 2014, and for the sea level, the full sea level physics in 2018. And again, this only requires 2 simulations. So we are able to actually interrogate what the 3D structure senses with our geodesy network. So this is quite exciting. So let's consider, as an example, this GPS station, Bear Peninsula, and ask what is its lateral and depth sensitivity, so its 3D sensitivity, to mantle viscosity structure. All right, so again, we think about our inputs. We require a spatial temporal history of ice cover. In this case, we're looking at the last deglaciation, so from 26,000 years ago to present, from ice 6G. And in this example, we're only going to consider 1D structure, right? So the accompanying mantle structure from VM5A. Okay. What do we get? So what I'm showing here is a plot of the sensitivity kernel, which is an indication of how much the GPS site senses the mantle, with the GPS site shown by the white triangle here. Okay. And positive values in blue indicate that as you increase the viscosity in a given grid cell, you're going to lead to an increase in uplift. In contrast, those in red, where if you increase the viscosity in that grid cell, you're going to decrease the observed uplift. And the pattern shown here is indicating a sensitivity to both the source, this ice and ocean loading signal, the surface load, as well as the receiver, the GPS station. Right, and before we focus on the near field signal, which is what we want to constrain, I will note that the color scale here is very much saturated. The sensitivity to the far field is about 2 to 3 orders of magnitude lower than the near field sensitivity. But one person's signal is another person's noise and vice versa. So maybe someone later on will use the signal observed in Antarctica to infer the Earth structure in the northern hemisphere. But we want to think about Antarctica. All right, so where is this station sensitive to mantle viscosity? So again, I'm showing this kernel, this estimate of sensitivity to structure at 300 kilometers depth below the Antarctic. And the sensitivity peaks right underneath the station and increases to a zone of about 200 kilometers around the station, which may reflect the resolution with which we perform this calculation. We can't rule that out yet, but we are pushing to higher resolution. And this central area is ringed by this opposite or compensatory sensitivity. So if we increase the viscosity right below the station, you're going to decrease the observed uplift, right? However, if we increase the viscosity in that peripheral bulge region, you're going to lead to an increase in uplift because it'll take longer for that mantle to move. Okay, let's look at what it looks like in depth. So I'm going to show a vertical cross-section through the kernel. So this shows with depth on the y-axis and latitude. So as you go south poleward towards the right, we can see what the sensitivity looks like. And again, it's largest right underneath the station, but it's extends for 1,000 kilometers away from the GPS site. So it's really sensing quite a bit of the Earth structure and can tell us quite a bit about the Earth structure, therefore. So that's pretty exciting. So geodetic data, this GPS surveying, can improve our understanding of the mantle. And with adjoint modeling, we can efficiently calculate the sensitivity of the GPS station to mantle viscosity and actually perform this calculation for realistic 3D Earth models. This can be used to inform GPS site selection and decommission. But our main goal here is to develop the first 3D Antarctic reference model via joint inversions with seismology, geodesy, and sea level data. Okay, so I want to talk a bit about my future trajectory. And you may have noticed from my talk, sea level is an inherently interdisciplinary, right? It's an interdisciplinary study. So my vision is to tackle problems related to the human condition with collaboration with both natural and social scientists. On the geophysics emphasis, I talk about how I'm building the Earth structure model that I wish past Evelyn had had access to. So I want to use it and I want to improve it, right? So I want to study how that structure is going to affect the cryosphere, how it's going to affect geodynamics and sea level modeling past and future especially. I also have this archaeology passion, right? I want to think about how the solid Earth impacted human civilization, how it impacted human migration, how it impacted the origin of agriculture, for example, how humans responded to their paleotopographies changing. So getting into it, one thing I want to look at in the near-term future is incorporating this 3D structure and satellite-based climate analyses. So we have satellites that are measuring deformations to the solid Earth, deformations to the equipotential surface, and they're being used to infer how much ice sheets are melting. So this is a picture of the GRACE satellite, which measures the Earth's gravitational field to infer how masses are redistributed over the surface of the planet. And one issue is that the current corrections for the last ice age, you have to correct for what the mass deformation is occurring because of the last deglaciation, which this is a big contribution. This is 10 to 40% of the signal. And those corrections are based on 1D Earth structure models. So there's pretty serious room for improvement in these corrections. And this is going to really update our sea level estimates for every major climate satellite using this 3D Earth structure model. And so this collaboration that I'm entering into conversations with JPL about, but especially the IceSat, so laser altimetry measurements of the surface of the ice sheets, as well as GRACE, so measuring the gravity change, with potentially, I think there's some exciting possibility of this NISAR being used to both see the structure and maybe even constrain it. We'll see. I hope it launches successfully at the end of this month. Okay. Stepping back into the archaeology world, one project that I'm actively collaborating with folks at the University of Washington is looking at the origin of human agriculture, asking how did Holocene sea level changes affect human settlement and migration patterns, particularly in Asia, which is her focus region. And so we've been working with two of her undergrads, and they've done such a great job putting together this new database of Holocene archaeology sites in Asia. And so my piece of this, I'm going to do sea level modeling of the different regions. I've taken a look at China. It's looking great. And comparing looking at how the quiescence or absence of sea level inundation might have affected the possibility for humans to develop farming practices. All right. I also love the field. I believe in data. I believe in data's ability to tell us more about the world. So I'm talking with folks who are looking at installing new stations, either GPS or new technology, which is very exciting, using radar returns from the top of an ice sheet to measure the deformation of the bed surface below it. The technology maybe needs a few years to develop, but we're working on it, right? So maybe we can get these uplift measurements from the center of the ice sheet. That would be amazing, right? Because currently we're restricted to anywhere that there's solid ground, a Nunatak, a little mountain sticking up out of the ice. But if we could actually measure everywhere on Antarctica, that would really improve our ability to use this GIA deformation to infer Earth structure. So I've taken a look at, in the site selection and decommission procedure, how the station density changes when you add new stations and how the sensing of the mantle changes as you add new stations. And so really looking at site selection analysis to optimize where we install, because the Antarctic fieldwork is, it's an ordeal. You want to make sure that what you install is useful. And so building on and improving our 3D Earth structure model is a major goal here. All right, and finally, proposal that I'm co-I on is looking at finding new archaeology sites using updated sea level and paleotopography predictions, particularly in Southeast Alaska. So asking, how did Pacific coastal societies adapt to rapid environmental changes, i.e. sea level changes, after the last glacial maximum? So that's collaboration with folks just across the river at Queens College and also University of Alaska Fairbanks. And another human migration angle is looking at the timing of the Bering Strait land bridge exposure. And this is on longer timescales. This is on millions of year timescales. And I'm also just so interested in looking at, like, when did these migrations occur? And this is collaboration with folks at UMass Amherst. Okay. So to wrap up, I argue that with accurate 3D GIA modeling, we can tackle big picture questions for the scientific community and for society at large. And this is modeling sea level response to past, present, and future changes to the cryosphere, and then also using these observations, such as GPS data, to improve our understanding of the mantle. So please feel free to reach me after the talk if you don't want to ask a question. There's me standing tall next to Celsius Rock. And I just want to say thank you, and I'm so looking forward to answering your questions.
Thank you, Evelyn. Why don't we, any questions from this side of the room? Younger folks. You check.
Oh, thank you for the great talk. So I think you mentioned a lot about 3D versus 1D GIA model, right?
Yes.
So, but I think 3D model itself have a lot of uncertainty. You talked about like a lot of uncertainty from seismic tomography, some uncertainty from water content, grain size, and some uncertainty about reality, right? What do you think about this uncertainty in 3D model itself compared to 1D model? Like 1D, 3D difference?
Yeah, that's a very good question, and such a focus of my PhD and such a focus of my work, right? So my goal is to get more data so that we can narrow that down, right? So if we're just using the laboratory inferences to convert seismic tomography to viscosity, we've got orders of magnitude to play with. So seismic tomography is going to give you a good picture of the pattern of viscosity variability, but it's not going to give you a good idea of the absolute value, right? So to that, you need to get measurements of the GIA process to constrain it. And so that's what we're really, really targeting. So instead of having a seismic tomography of the Earth, having a GIA tomography of the Earth and actually get down that viscosity value. Yeah.
Thank you. And also a follow-up, like when you're talking about GPS, present day uplift rate, right? How do you separate there's uplift rates from, let's say, elastic signal from earthquake signal to constrain your viscous signal?
Oh, that's a great question. So one exciting area of research that a friend of mine is looking at is using the viscoelastic deformation following earthquakes to infer the viscosity, right? One kind of interesting part there, though, so the viscosity that you might see after post-seismic relaxation, that may not be the same viscosity that you would sense for a forcing that's acting over these sorts of timescales, right? Harriet Lau's done a lot of work looking at how the viscosity is going to vary with the different timescale forcing. So I invite you to check in with her on that one. I don't want to steal her thunder. But yes, I think that there is a lot of work that can be done with seismology and not just tomography. Yeah.
Ben.
Hi, thanks. I really enjoyed that. I was wondering, you alluded, talking with you, showing to global view of Earth's viscosity. So I was just wondering, is part of your vision to go beyond understanding what's beneath the Arctic and Antarctic, and sort of what your roadmap would be towards understanding mantle viscosity structure?
Yeah, absolutely. Thanks. That's a great question. Oh, I should ask, can folks online hear the questions or should I repeat it?
You might want to repeat.
Okay, I'll repeat it. Yeah, Ben's question was, am I focused on the Antarctic and Arctic in particular for this sort of GIA imaging, or do I have a roadmap for looking at other places as well? Yes, I do. So actually, I talked about my work with Jackie and Andrew Lloyd. I have a separate project funded by NASA working with Jim Davis, who's a geodesist at Lamont, specifically looking at the Bifrost experiment in Fennoscandia. So this is sort of the gold standard of GIA geodesy data in the planet, right? This is the longest running geodesy experiment that's been measuring for, going on 3 decades now, the crustal deformation there. So I think that I'm really learning like what GPS can say in sort of like the best case scenario there. Like that is the cleanest, most beautiful geodesy data set that we have. So yes, I am looking at other regions of the world for sure. I think anywhere that there is or was ice. I think I'm limited to Fennoscandia, Greenland, Alaska, Patagonia, Antarctica, because I'm looking at how this all changes with ice. So yeah.
There are other types of loading.
Oh, for sure. Yeah.
You could even think of loading on planetary bodies.
Yeah, actually. So there's a Professor Lamont looking at deformation due to the river delta formation, right? So coming off of the Himalayas, there's the deepest delta formation on Earth, and in that case, you have loading sufficient that maybe you do need to, and he's talking about looking at 3D structure modeling in order to get that response correct. Yeah, so that's true. Yeah, it's not just ice. It's any time that you have a surface load of sufficient size to deform the mantle. Yeah.
Thank you. I really enjoyed that. So, talking about this is not strictly research related, but more of a geoethics question, which you kind of talked about with some. So the project you have in Alaska, are you incorporating like indigenous voices in that as well?
Yes, we absolutely are. So for both of them, actually. So So I'm thinking about the sea level inundation flooding in the Bering Strait on this side, but there is definitely involved a native researcher. I think he's actually on the Russian side. He's not an Alaskan native, but he is, yes. I think that's so important. Yeah.
Thank you.
Ying and then Yushin.
I'm just curious, do you have any plans to look farther back in time? How does the viscosity, mantle viscosity, how did it change? You had an initial condition problem there, right? Where do you start? What is the time scale of viscosity change?
Oh, that's a great question. Okay, so the question for the audience, sorry I didn't repeat the last one. Thinking about further back in time, when did the viscosity change further back? Is that
Well, how did it change in time? What's the
How-
time scale of changing? Is it very, very slow? So you can
Yeah.
assume constant over the last 21,000 years.
Yes. What is the time scale of the mantle viscosity changing? Yeah, no, so one interesting lines of evidence that the Earth's viscosity had to have changed, the thermal history of the planet, is looking at the moons moving away from the Earth. As you back in time, track back, because of tidal forces, the moon is actually getting further and further away. If you, due to viscous deformation of the mantle, right? If you backtrack what, using today's viscosity structure, what the moon's position would have been through time, it actually crashes into the Earth. So we know that there must have been a change in the thermal history of the planet and therefore the viscosity structure of the planet, because otherwise, yeah, the data just doesn't work. So I think that there was a change from, say, stagnant lid or sluggish lid mantle viscosity deformation and plate tectonic style to a more present day style plate tectonic style. Somewhere between maybe 2.5 billion years ago. So that was definitely a transition in the viscosity style. But in terms of where we are now, I think certainly for GIA problems, we can think about the viscosity snapshot being accurate. If we want to think about even further back in time, so for example, geodynamic modeling, and looking at how the surface of the planet changed and potentially led to conditions conducive to ice sheet nucleation, yeah, I think then we do need to think about how that viscosity might have been different in the past. Yeah.
Leslie?
Something I was kind of wondering about. So if Antarctica only had about 5 meter ice, basically there would be no flexure, right? So there's that elastic portion of the lithosphere that is controlling how much flexure you get and how much, isostatic response you have. And so, given that the flexural rigidity itself is a function of elastic thickness, how are the viscosity constraints? How is the elastic thickness constrained or taken into consideration when you're inverting for viscosity using GIA?
Yeah, that's a great question. So I think, so the question is, how is the elastic structure taken into account when inferring or imaging the GIA structure? Yes, so our calculations are entirely viscoelastic, so we have to take into account the elastic structure as well. And it's not just there is the flexural component of the very cold portion of the outer mantle, but it's also elastic contraction of the entirety of the crystalline lattice, right? Like the solid Earth is solid. Those crystal lattices are compressing. And so, yes, we're not able to have a world that isn't elastically deforming. We're just able to say, like, this is deformation due to the mantle moving, flowing.
Wait, so in other words, the elastic thickness of the lithosphere is not taken into account?
No, it is taken into account, absolutely, yeah. So one thing that we do is have different lithospheric thickness models and test that, and that's something that we look at quite a bit, yeah. West Antarctica is interesting in that it's this failed rift system, right? So the elastic thickness there is very, very thin, right? Like there is volcanoes poking out of the ice sheet right now because it's been pulled apart, stretched apart, and there's very elevated geothermal heat flux. The ice sheet is being melted away from below. Yeah, it's just a very fascinating rift system setting.
Jim, have you considered looking at some critical areas in the East Antarctic ice sheet, particularly Aurora Basin? That's potentially recently discovered as going to be a major component to
Yes.
Sea level rise.
Yeah, so the question was, have I considered looking at East Antarctic regions, which could be a very huge contributor to sea level rise? Yes, absolutely. So I think that you need to care about anywhere that there is a marine-based ice sheet, where that ice sheet is grounded below sea level, where if it wasn't there, that would be open ocean. And so there are the Aurora Basin, the Wilkes Basin, there are regions in East Antarctica that can be huge contributors to sea level rise as well. And so yes, those are targets of study. And we're talking with the Australians actually are the ones who particularly survey those regions. And so yes, we are looking at East Antarctica too. Yeah.
Mark,
What are your initial findings regarding sea level and the advent of agriculture, etc.
Oh, that's a great question. So what are my initial findings with sea level change and the advent of agriculture in Asia? Yeah, so we've looked at China in particular was our first area of study, because that's my collaborator's primary focus region and where she does active archaeology digs. And if you look at the relative sea level data there, what you find is that sea level was pretty flat through the Holocene, and you want pretty flat sea level changes. You want your coastlines to be pretty quiescent. You don't want to have major flooding events pushing you out and flooding your civilization and then moving out again. So in China in particular, we find that there were conditions that were suitable for the formation of agriculture. There were stable conditions, and this you would not predict with sort of a global average view of sea level change. So if you do our sort of like out of the box GIA modeling and predict, you would actually see pretty significant flooding of China, which the sea level data doesn't support. So we need to have more regional focused structure models. The caveat to that is that this area is very easily flooded. It's very low lying, right? And so we want to contrast the sort of stable conditions that were conducive to farming with what's going to be happening in the coming century, and show that no, we were able to have farming because it was very stable, but it's going to be flooded quite quickly. Yeah.
Okay. Does he want to unmute, or do we?
Did you put the volume up?
Yeah, you should be able to. It's on the default setting, so you should be able to talk.
He's talking, but we can't hear it, so.
Well, can you? I don't know. We can read it. Chat.
Yeah, we can't hear you. If you can type.
No,
read
I don't
it.
think it's on.
While he's typing to someone else.
I want to follow up on Ying's question. You show the Lysakian rainbow change through time. Will the viscoelastic properties change, particularly in North America, if you have large ice sheets coming and going and coming and going? Does that weaken or strengthen the lithosphere if you're loading it and unloading it, loading it and unloading it?
Got it.
Like a bone heals
Yeah, no.
stronger in the break.
Yep.
Will the rocks heal themselves, or do they just become weaker and fail much more quickly?
Yeah, that's a great question. So looking at how does the actual mantle properties change as you have this repeated forcing, this repeated waxing and waning of the ice sheet? Yes, so that is something that we were looking at. Again, Harriet Lau interrogated, and what you find is when you have this repeated forcing, you're going to damage the mantle lattice, right? So you're going to lead to smaller crystals, which is going to change the deformation mechanism. It turns out that that signal is much smaller than the temperature change that you would experience. So yes, that is something in there. I think it's going to be a second or third order signal, whereas how much a material can deform when it's hotter versus colder is going to really swamp that out, is what we found.
Is
Bob said he'll type it. It's a long question. He'll ask later.
Okay.
Okay. Well, we're at almost lunchtime, so let's thank Evelyn one more time.
Thanks, y'all.